So, in the last class we talked about the various attributes of turbulent flows. We cataloged some of the characteristics of turbulent flows, and one of the attributes that we talked about was that it is not a molecular phenomena. You can see it in the macroscopic level. So, you can write down the continuum equation, and that would still be valid equations for turbulence. So, that is why this is always understood that if you look at Navier-Stokes equation, that should explain turbulence adequately. Okay. So, suppose we are looking at turbulent flow at low speed, so that incompressibility holds, then these are your momentum and mass conservation equations giving rise to Navier-Stokes equation. Okay. What we have done here in writing the momentum conservation equation, we have added this time dependent body force term, which is given as a function of position x and time t for all the points in the domain omega, and the boundary condition is given by boundary is located at del of omega. Okay. So, this is what we have. So, this is your problem statement. Now, once you have this, we need to find out how the solution of these equations can describe those features of turbulence that we talked about. One of the earliest attempt in this direction was made by Reynolds himself. What he proposed was that this space time dependent velocity field is decomposed into two components. Okay. One is the time independent part or the time averaged part, and the other one is a kind of a fluctuating component. Okay. So, when we are talking about a time averaging operation, this essentially is indicated by this angular bracket. That would involve you take the signal here, integrate over a large time, and of course, you divide by the time span, and in the limit tau going to infinity, whatever you get, that is what you are calling as capital U of x. So, this is your mean flow or the time independent flow part. Okay. This was what was originally done by Reynolds, and it is called double decomposition, because you are taking the full flow field, splitting into a time averaged part and a fluctuation part. Additionally, what Reynolds did, Reynolds basically said that this time dependent part is truly random. So, what does it mean truly random? Means if you take its time average, it will be equal to 0, right. So, this is the way that when you split a stochastic quantity into two parts is what we will call as Reynolds splitting. Okay. Now, let us look at the corresponding boundary conditions. How do we apply those boundary conditions for the velocity field? Now, we have split the velocity field in terms of a time averaged part and a truly random part. Then suppose this turbulent flow is generated by a flow condition where your boundaries are not articulated. Okay. So, the boundary motion is precluded. That means what? That the boundary conditions are going to be time independent. So, if that is so, if you are looking for such a flow, then this the mean u would satisfy those time independent condition, because that is the way we have split it. What will then remain of for V? V is the fluctuating quantity. So, all the boundary conditions is taken up by your capital U. So, V ends up satisfying homogeneous boundary condition. Okay. So, this is the story, but there is some bit of philosophical mulling that we can indulge in at this stage. We are talking about turbulence to come out when we have not done anything to the flow, because the boundary conditions are time independent, but still somehow the flow has become time dependent. We at least have some clue where it has come about. It could be because of flow instabilities, right. Flow instability is something which we have seen can lead to that. But looking at it from the receptivity angle, we also know that if we eventually have gotten into some kind of a time dependent motion, there must have been some kind of an excitation which was time dependent. But this is for a long time held view that turbulence comes about out of nowhere. So that is what this boundary condition and the splitting is indicating. So, now we should keep this in mind then, that the fluctuations satisfy homogeneous boundary condition, and the total boundary condition is time independent, and that is totally taken up by the mean field. So, there are these possibilities. If we have U specified, that is a Dirichlet type of boundary condition on the boundary, then the V vanishes there. If on the other hand, if I prescribe some kind of normal derivative for U, then the normal derivative of V will vanish, because whatever the normal derivative is given for the total field, that is also again taken over by capital U. So, V ends up always satisfying homogeneous condition, either in terms of the variable itself in the form of Dirichlet condition, or in terms of derivative condition, the Neumann condition, right. Now, if we are talking about a total flow field that is periodic, then that periodicity would come about from the geometry of the problem, and that would be totally taken up by both the mean as well as the fluctuation, because you cannot say like the periodicity is completely taken over by the mean. Then if V is not periodic, of course, then on the total field you cannot have periodicity. So, V also has to be periodic. So, please do remember that these are the three possibilities for the fluctuations. Now, having described this, let us go ahead and look at our Navier-Stokes equation with the help of that double decomposition we talked about. If we do it, we are going to get an equation of this kind. Well, how does it come about? We have this condition we are writing the Navier-Stokes equation, the momentum equation in this form, with the body force term kept here, right. Now, what we have done here basically, so this is that U dot del. So, now U itself we are writing it as capital U plus V. Please note that unlike what we did for instability studies, V is fluctuation, but we are not talking about small fluctuations. In turbulence, the fluctuations are of the same order of magnitude as the mean itself. So, that is why there is no need to put some epsilon or anything, it does not hold. If I now substitute this kind of decomposition in this, what will happen to this term? This will be this. Right. So, by definition, of course, this is 0 because u is the averaged time averaged quantity. So, it is not a function of time. So, that goes off. Now, if I average this equation, so that means what? I will be averaging individual terms one at a time. So, if I do that, so we are talking about this. Okay. So, this will be this. Now, what happens is we make a supposition that the time averages of time derivatives vanish. May seem troubling. In a computing course, we do not go that deep, but here we can afford to explain it a little better. Why? Because when I am talking about time averaging operation, what was the definition that we talked about? This is the limit tau going to infinity 1 over tau integral u dt, and this is going from 0 to tau. That is your definition of time average. Now, what is this averaging operation? Averaging operation is over a very large time. If I am talking about a very large time, what is the corresponding frequency? Frequency is going to be very small, right? Whereas, the fluctuations that we associate with turbulent flows are characterized by very high frequency oscillations. That is why we call it chaotic or random. So, what happens is, even though we are looking at a time dependent motion, there are two types of time variation. One is happening over a very large time. That is what this time averaging operation is suggesting, and another is that very high frequency fluctuations that is characteristic of hydrodynamic turbulence. So, these two frequency scales are widely separated. If that is so, we could treat them independently. Okay. This is also is the gist of what people talk about, theory of multiple scales, isn't it? We are having different types of time scales. One is happening over a very small frequency, very small time scale with very rapid fluctuation, another is slowly varying. In fact, that is one of the reasons that people have gone ahead and started talking about unsteady Rand's equation. We have not talked about Rand's equation. Now, we are seeing what is the philosophical justification of talking about an unsteady flow. So, this is what we are talking about, the supposition that if we are looking at the time average quantities associated with the time derivative, this fluctuation, the derivative, where would it come from? It would of course come from those high frequency fluctuations. That is what rapid time variation is about. Whereas, this operator, angular bracket operator, is happening over a large time. So, that is what we are saying, that this term will have to go to 0, right. You do not have to really struggle very hard to think about it. Think of even a simple harmonic variation of say V. If it is so, then what we are talking about we are going to write about del v del t here. Del v del t will be something like I omega v hat, the amplitude, right. And then we are going to do this operation 1 over tau and tau going to infinity. And if I take this thing, what happens? Over one cycle, it is going to give me 0 contribution. So, even if I take to a very long time scale, I may have at the most a fraction of a time scale, because every time scale will cancel each other out. And then if I am getting that contribution and dividing by tau, and that tau is very large, it does not give you anything. So, now you understand why this term does not survive also. So, that is what will happen, that when I am time averaging this equation, I am not going to get any contribution coming from this, right. Convinced? Now, look at the other term. We have to be doing this. Well, we will just split it into this part. So, we are talking about here u plus v with a dot product, nabla. This is operating on u plus v. That is what we are doing. So, if I do that, I am going to get here one set of terms u dot del u, this is this term. Then I will also have a term which is like this u dot del v, this term. Then I will have v dot del u, this term, plus v dot del operating on. Now, it is very easy for you to suggest to me that these are time independent. So, averaging operation will not do anything. So, this transmits itself as it is. Right. What about this term? This is a time independent quantity. This is the random quantity. So, if I do the averaging operation, again this will goes to 0, right. So, this goes to 0. What about this? This also goes to 0. This does not. This does not. This remains like this, v dot del v. So, of course, in this equation, this first bracket gone missing, but you can think of v dot del is the operator operating on v. Okay, so that is that. Now, what has happened is I could similarly write this term del p by rho. If I do this, what will I get? Del of this p, instantaneous p that I am writing, is this plus some kind of fluctuation, which let me write it as this. So, this fluctuating pressure would be a function of position and time. So, any time dependency of pressure would be embedded in p prime, okay? And it is incompressible flow. So, we do not allow any fluctuation in rho. So, that remains as it is. And you can see this is the time independent path. So, this will give me nothing but grad p by rho. What about this term? the fact that pressure fluctuation is also random, and if I am doing a time averaging operation, this also should go away, right. So, we do get that that this pressure term will just simply give us the gradient of P by rho, that is what we get. So, the convection term has given us two terms, one is directly coming from the mean, another is coming totally from the fluctuation. This is the mean pressure term, this is the term that we are going to get from the viscous term, this term, right. So, that term is also very easily understood. We are talking about nu times del square u operating it, and that will give us nu times this plus nu times once again you can very clearly see this will go to 0, right. So, only this will remain, and that is what we have given. Well, I admit that we should have indicated this by a different symbol, because that term is coming from here. So, what that term gives us, we should write it like this, 1 over rho f time averaged term. Let me call that time average term in terms of f hat. This is that. Okay. So, please do note that this is not quite right. I should indicate it by its time averaged, because we talked about it. We talked about it that the body force is basically a space time dependent function. So, we need to talk about its time average. Now, this directly comes from mass conservation. Without any difficulty we can understand it, and the pressure is what we have defined here. So, there is no difficulty in understanding that. Now, let us see what we get. We have obtained the total equation, and then we have also obtained the mean equation. So, if I write down the mean equation, so I am going to get the following term here. From here we have seen that this works out right, del u plus v dot del this is that, and here we are going to get del of capital P by rho, and here we get mu del square capital U, and this I will write 1 over rho, we called it as f hat. Now, what we have seen that we have split the total variable into this part. So, what I could do is I could try to write out a dynamical equation for V itself. What do? I just simply subtract this one from this, right. If I do that, what would I get? This, imagine, I mean, remember this is a time averaged equation, while this is a actual virgin equation without doing any operation. I mean, this is the instantaneous equation. So, I can subtract this from this. Then what do I get from here? I will get this term del v del t, right. So, I will get del v del t term. Now, if I write this equation here without doing any averaging, this is what we are going to get, del v del t, and from here what do we get? U dot del u plus, I have written those terms. So, I will just write them down once again. and there isn't much of a problem in doing that. U dot del operating on V, then B dot del operating on U, and of course I have B dot del operating on V, and that is equal to minus del P by rho plus minus, I would write del, what am I writing there? Well, I could write it here as del P prime by rho and nu del square U plus nu del square V, and then of course I will write 1 over rho f hat plus f prime by rho. So if I now subtract this from there, which are the terms those are going to go away? Well, on the right hand side, this goes away with this, right? So that's what we get. What do we retain? And we then get to retain this, all these three terms. Please do understand that this term and this term are not same. This is retaining all its time variations. This is the corresponding time average term. So that's why both of them would be there. This plus this, both of them are there. And these two are those terms which are here, this and that. This and that, they appear there. Then of course I could see that this one will cancel, so I will get minus del P prime by rho, or I could write, instead of writing del P prime, I will write del of P minus capital P. That is your P prime anyway. And this part will cancel. Right? This part will cancel, and this part we have said already they have cancelled, retaining this. So this is the term that we are going to get on this. Right? What about this term? Now do understand, the body force is not an attribute of turbulence. What is the turbulence that we talk about? Turbulence is an effect. What are the causes? How the turbulence is caused? By all those inputs, and one of the input happens to be the body force also. So we are not talking about a body force which is random. We are talking about some deterministic, but it could be time dependent body force. So if I talk about that, then what happens? There is no such thing as fluctuating component of f prime. That is why we did not write anything here. So this is something that we understand, but I must also remind you that we can talk about fluctuating body force itself, and this is what you do in Fokker-Planck equation in physics, but we are not going to go through that route. So we will not talk about Fokker-Planck equation, but we will just simply say there are no fluctuating body force. Okay? So we will say this is non-existent. Okay. So basically then we have been able to write out a dynamical equation for the fluctuation, and this is the corresponding mass conservation equation. So these are the two sets of equations that we have written down for this. The previous equation that we had written, this equation 4a, defines the time averaged field, and that is why that equation is called the Reynolds average Navier-Stokes equation. It is a time averaged equation. It was proposed by Reynolds, so that is why I call it as Reynolds average Navier-Stokes equation, or RANS. Okay. However, what we have noted in that equation, well, we have it here. We have no clue to this term. Immediately we do not know what it is, because this is related to the fluctuation. What is its physical nature? What is its physical nature? That this is like your stress term, right? Stress term that we are familiar with. Even in laminar flow we have this stress term. So, here also we get this. This is nothing but V I V j kind of term. So, that is what it is. So, these are some additional stress term, or you could even visualize it as some kind of applied body force, right. So, you can term that as either a additional stress term or a body force term that arises due to turbulent fluctuations. Okay. This additional stress are known as Reynolds stress. So, this is what was originally suggested by Reynolds. However, we confess that a priori we do not know what this is, and this has been the intense focus of many research work going on the topic of turbulence modeling. In turbulence modeling, we try to model this term, because this is not known a priori. So, we do have to supplement it with the help of some additional phenomenological information or some ideas based on theoretical fluid mechanics. However, I am not going to talk about turbulence models any further. Okay. So, what we have now, we could also write down the same equation. Here we have resorted to vectorial form, right. We have used vector calculus, but we can also use tensor notation to write it in terms of this. So, you can very clearly see local acceleration, the convective acceleration, and this is a stress term. If you recall, before Navier-Stokes equation was written, this equation was in vogue, and this is attributed to Cauchy. So, this is also called the Cauchy equation. Okay. What Navier and Stokes did, which many people do not understand, that these two scientists, they related this stress with strain rate. That was that. Without that, this remains as if it is an additional unknown, right. And this is of course the body force term, and this is the mass conservation term. So, that is what we have. We could write it in this form. We will use both this notation because it becomes easier for us to handle. We are familiar with the fact that whenever indices are repeated, that implies that you sum over that index, right. That stress tensor sigma j is written for a Newtonian fluid like this. So, the stress tensor has two components. One is when there is no fluid motion. So, that is given by the hydrostatic component, and this is due to the motion, and this motion is for a fluid which has a specific characteristics which was originally suggested by Newton himself. So, any fluid flow which satisfies this paradigm is called the Newtonian fluid. What it essentially does, basically it does tells you that the stress is related to strain, and you are so much used to hearing that stress is proportional to strain, you automatically tend to think that that mu is some kind of a proportionality constant, which is really not strictly adequate or correct thing to do. Why? Because here we have a tensor of rank 2, this is a tensor of also rank 2. At the most or at the least, mu should be a tensor of rank 4. So, basically it is like a dot product that you are taking. So, mu matrix, it is a 4th order tensor taking a dot product to give you another 2nd order tensor, right. That is what you do in a vector equation. You just do not write one vector is proportional to the other. You always see that Navier-Stokes equation is that when you are writing say del v del t local acceleration term, that comes as a sort of a contraction term from the convective acceleration term that involves a dot product of a stress term say vector, right. So, vector is a tensor of rank 1. So, that is what you get. Anyway, we will not quibble about it, we will go with the crowd and say stress is proportional to strain. That is precisely what Newton did himself. He took the simple example of quiet flow and then said, okay, I apply this strain and this is the stress appears. So, these are proportional and this is a proportionality constant. It is not. There is a very beautiful theory developed from theory of elasticity, which talks about how to relate stress and strain, and this is what is called as constitutive relation. So, the constitutive relations are necessary to propose a relationship between stress and strain, and in developing those constitutive relations you can invoke certain properties, some of which comes naturally for physical variables in terms of symmetry, isotropy, etc. That brings down the number of unknowns. Is that tensor? How many components would we have for a 4th order tensor? It will be 3 to the power 4, that is 81 components, and with all these concepts of isotropy and everything, we can actually bring it down to only 2, right. And in fact, you are familiar with the Stokes hypothesis, which even brings down this 2 quantity into 1. So, we are familiar with that in basic fluid mechanics, so we will not go through that. S tilde ij is your rate of strain, and that is defined as this. Okay. So, this is something like a average angle at a interstice of a. So, what happens is we have a stress term. We can also perform a Reynolds decomposition in terms of a mean component and a fluctuating component, where the mean component itself will have the hydrostatic part plus a mean strain rate, right. Okay. So, we will expand it little further. Okay. So, you can see that the total stress would be split into mean and fluctuation. The mean would be given in terms of the hydrostatic component and in terms of the mean strain rate. So, the mean quantities are all defined in terms of capital letters. So, capital Sij represents a mean strain rate. So, this mean strain rate we should be able to define it in terms of the mean component of the velocity as indicated here below, that the mean strain rate is given as average of the angular rotation at this corner of a let us say a small fluid element, and the fluctuating stress part also would be contributed by a fluctuating pressure and the fluctuating strain rate. So, the fluctuating strain rate would be given in terms of the fluctuating velocity component, right. So, that is what we get. There is sort of a mistake here. This would be also lowercase x. Okay, it is basically the same independent variable, space variable we are talking about. Now, what we need to do is, having done that, we could write down the mean equation, that Reynolds average Navier-Stokes equation, also in this particular form. Okay. So, this is your convective acceleration is equal to 1 over rho. Now, please do understand that in writing this term, we have put the Reynolds stress term inside, and this mean stress, this two together is what we call as the total mean stress Tij. Okay. So, this is a tensor of rank 2, which is contributed by the hydrostatic pressure, the mean strain rate, and the Reynolds stress. Okay. And this is the corresponding body force term that we have. So, this is an alternate way of writing out the Rance equation. So, we find that because of turbulence, we have those fluctuations which we call as V vector, or in tensorial notation V I components. So, this dynamically has a dimension of stress term. So, rho times V I V j, and we have taken a time average. So, this is what we call as the Reynolds stress term, we have already noted. Now, when we write down the governing equation for the fluctuation, that is written here, right. So, if I remove all the terms which are not there, so this of course goes away, this goes away, this goes away, this goes away, this goes away. So, this is what we have, right. So, this is your governing equation for the fluctuation, that is what we are talking about here. The fluctuation, the dynamical equation of the fluctuation is driven by what? The mean flow, okay, and also by pressure. Because of the way that we assumed, we proposed the body force not to have a fluctuating component. So, body force does not come into picture at all. So, that is what we are saying here, that the fluctuations are driven by mean flow and pressure field, rather than being directly driven by the body force or boundary condition. Why not boundary condition? Because we have seen already that boundary conditions for V are most of the time homogeneous, whether it is a Dirichlet or a Neumann type, it will be homogeneous. So, boundary condition really does not drive the fluctuation. So, please do understand, this is very, very crucial, that in a turbulent flow, what we see as a fluctuation, that fluctuation is driven by the mean flow itself, and also of course, the applied pressure gradient. Body force per se does not give rise to turbulence. In fact, that is one of the reasons that when we talk about water waves, there the whole thing comes about because of the Coriolis term. That is like your body force, that does not directly contribute to turbulence. Turbulence has to be contributed by the mean flow, the instability of the mean flow, and the pressure gradient that is implied there. Okay. So, do understand this, that whether we solve the Rance equation in the vector form or in the tensor form, we need information about this term. We have no other recourse. We have to get some information about Reynolds stress. Now, how do you get the Reynolds stress equation? It is a basically second order quantity. We have written down the equation here for the fluctuation itself. So, I could write it in terms of in a tensor notation form, right. So, what we are talking about then, let me just clean up this bit, and then we see if we write it in terms of tensor notation, then I would perhaps write, let us say, the ith component, then I will write del vi del t plus ui del well, let me call uj del xj operating on vi, that is this term, right. What about this term? This term also I will write vj del xj operating on, say we are writing it for the ith component, right. So, here also I will write here as ui. Okay. What about this term? Well, this term is going to be vj del xj, and this is operating on vi. That is that, and on the left hand side I will have, basically I will write this as 1 over rho del p prime del xi, right. We are writing the ith component equation, and from here we will write nu times del square vi. So, this is your ith component of the fluctuating quantity. Now, let us try to write out an equation for Reynolds stress. So, what I do? I multiply this equation by, let us say, Vj, right. So, basically what I am going to do, well, let me just to avoid conflict, let me write here this repeated index by some other notation, okay, so that we do not have a conflict here. Okay. So, this is the so what I do is I can multiply this Vj, and then we time average, because we want to get an information on the time averaged quantity. So, if I do that, of course, I am going to get this as Vj del Vi del t, then we have Vj and Uk del xk of Vi. So, that is what we have, and from here we will have Vj Vk del Ui del xk, right, and here we will get Vj Vk del Vi del xk, and here we will write Vj by rho del p prime del xi, and here we will write nu times Vj del square Vi. Now, what we are going to do? We are going to time average this equation. Now, what we are going to get, this term can be written in terms of del t of Vi Vj minus some term. So, I can get that. So, I probably can contrive it to write it like this, del t of Vi Vj minus, say, Vi del Vj del t. This I could write it like this, isn't it? I could do those similar things, but when I actually now time average this equation, again we will talk about this term will give us what? This term will not go away, right? That will tell you how the time average of Vi Vj changes with time. So, we'll have to talk about this time average minus this time average, and this will be, let us say the mean flow is given to us, but still we will have to be performing this V j u k del V I del x k . Now, this also would come in here like this V j V k del u I del x k. But look at this term. Here we have V j V k del V I del x k. So, I will have those other terms written on the right hand side. So, in writing down an evolution equation for the second moment, so V I V j is the second moment. If I do that, I see immediately that here I have a triple product term coming here, right. So, what is happening is that in writing an equation for the second moment, we need information on the third moment. So, it is not very happy situation that when I am looking for the first moment equation, that is what our Rans equation was, is not it. So, in writing the Rans equation, we had understood the need for modeling the second moment, that is a Reynolds stress equation, and when I try to write down an equation for Reynolds stress, I need to get information on triple correlation term. So, this is what is called as a turbulence closure problem. At whatever level you look at, you will have always something which is not known at the higher level. So, you know, for a long time, especially people emphasizing on the experimental aspect of turbulent flows, they kept on measuring various moments of turbulent flows with the hope that after some level those higher order correlation terms are not going to be important. So, you could stop at somewhere, and then you do not have this problem of turbulence closure problem, because it gets over. Suppose at this level, suppose I could have said this term is 0, then my problem is solved. I have been able to write out an equation for triple correlation term. Okay. But it is not possible. In fact, you would note that there is a major activity in turbulence modeling, where people do write down this equation for Reynolds stress directly and try to solve this equation. But please do mind remember that in writing those equations for this triple correlation term, they need to do some kind of modeling. So, it is not a priori that you are going to do completely an analytic solution, get an analytic solution. You will have to do some kind of empiricism, some kind of modeling, or take help of some experimental input to close the problem. But otherwise, turbulence remains stubborn because of this closure problem. Okay? It never disappears. So, that is what we note, that if we want to make any progress, some closure of the hierarchy must be introduced. This is what is attempted in most of the turbulence model, and what is interesting is people do not want to go into third order terms itself, but be happy with the Reynolds average equation itself, and then try to relate Reynolds stress with the mean strain itself, right. This is something that we need to touch upon next when we meet tomorrow, right. Stop here.